All right, this next chapter we're going to look at is on waves. And not that we've learned everything there is to learn about electricity, but we got to draw the line somewhere. And there's a lot, I still want to talk about and involving other units. All right, so a wave, let's start with the definition. And we'll start off with one that really, because this chapter is really about mechanical waves. And this means that the wave is made up of the matter it moves through. So this is like saying a water wave is composed of water. A sound wave is made up of air. A string wave is made up of string. So let's write a definition for this. All right, so it says waves that involve the motion of a substance through which they move. So the water moves up and down as the wave moves left and right, or moves forward. This material they move through, or the substance they move through, we can define that too and call that a medium. Whoops. The substance a wave moves through. All right. And we can, kind of link these together about, I guess, these examples of mechanical waves that I said, the medium, or talking about mediums, right? So the medium of a water wave is water. And that's what makes this a mechanical wave. The medium of a sound wave is air, usually. You could, because sound can travel through solids and liquids. All right. And the medium of a wave on a stretched string, a wave on a stretched string is the string. Okay. That's good. All right, let's get another definition, because usually, although we're talking about mechanical waves, I sometimes like to get even a simpler definition of just a wave. You might say, well, what's a wave that's not a mechanical wave? That would be an electromagnetic wave like light, radio waves, X-rays, infrared, ultraviolet, microwaves, gamma rays. All right, so we'll come back. We'll talk a little bit about that too, or I'll mention it here in a little bit. So a wave. Why am I putting numbers here? I don't know. My notes have numbers next to them, so it's kind of the order I wanted to talk about them in. And so I took some notes about what I wanted to tell you guys before I made this video. A wave then is a disturbance. In a medium that carries energy. So a disturbance in a medium that carries energy and I guess I could say from one location to another, or that just carries energy. So a disturbance in a medium that carries energy. And that's kind of a key idea, is that the energy moves, not the medium. The medium does move up and down, right, in a water wave, but the water itself doesn't move into the shore. So that's kind of what we're getting at. So is that the energy moves, not the matter. And maybe I'll just write that down. Energy is what moves. And I'll just write not matter. So once again, the water moves up and down, but the wave moves forward. I'll mention this earlier. I think about it like if you ever go to the beach and you throw a football out in the water, it doesn't ride the next wave back into shore. If you throw a toy to your dog or something to go fetch the toy out in the water, it does the toy stays out there, right? It doesn't ride the next wave in. All right. So there's some definitions to kind of think about going forward, what a wave is. So we create a wave by a disturbance in a medium. It carries energy forward. Waves that are made up of the medium that they're made of are mechanical waves. All right. So let's go ahead and get some characteristics then. I think we have everything I wanted to talk about. I guess I can go ahead and I might as well mention what little I wanted to say about electromagnetic waves right here also. So and just maybe a couple other things, that when we talk about sound in this chapter, before I go on to characteristics, sound waves are made up of air, right? Or I should say, for sound waves, air is usually the medium. And I think I already said this before. But a key idea with that is that you can't have sound in space, right? So in outer space, we're going to have no sound, right? Because if we don't have those air molecules or any molecules at all for the sound to travel through, then the sound can't travel through space. Sure, it can travel through solids, right? But it needs to have some kind of medium for it to travel through. So you wouldn't be able to hear in space because there's no air molecules there for the energy to be transferred through. So we like to refer to something like outer space as a vacuum with no air. All right, I think that spelling's right. Okay, so can waves travel through outer space, right? And right away we have to say yes. So electromagnetic waves are those other waves that are not mechanical and can travel through outer space. So electromagnetic I'm going to go ahead and can travel through outer space. And types of electromagnetic waves, we've got radio waves, Got microwaves. We've got infrared. We've got, I'm kind of running out of room here, visible light. And this would be your spectrum of the rainbow here. So Roy, G, Biv. So red, orange, yellow, green, blue, indigo, violet. Beyond this, on the other side of red was infrared. So on the other side of violet is ultraviolet. And then beyond that, we have X-rays. And then, oh, I'm running out of room. The last one would be, I guess I can write it this way, gamma rays. All right, so this is called an electromagnetic spectrum. And I wrote this in a certain way where the longest wavelength, the lowest frequency, and the lowest energy are all on the left. And on the right then would be the highest energy, or the highest, yeah, I'll write energy first. Highest energy, the highest frequency, and the shortest wavelength. All right, so these waves, or this type of light, right, this is all electromagnetic radiation. These are the different forms that light can take. When they're over on this side, it is high energy, right? Short wavelengths, high frequency. And these are more dangerous, right? So UV light from the sun is more dangerous for this reason. And X-rays, obviously, you know, if you go to the dentist and get an X-ray on your teeth, you'll wear a lead apron, and the hygienist will go in a room outside so that they're safe from the X-rays. So you get the idea, right? And then over here, these radio waves are totally, you know, are pretty harmless, right? This is how our cell phones communicate, and our remote controls communicate using radio waves. But it is a spectrum, so there's no clear frequency that where, well, the frequency gets greater to a point and becomes micro. It's a spectrum. It's so it's not a clear line, but there are certain sizes or amounts of the frequency that allow it to be micro, or allow it to be radio waves, right? So anyhow, we'll come back and talk about this here eventually, probably when we get to the next chapter. Okay, so characteristics of waves. Let's move on to that. And I think I'm going to snag another sheet of paper here if I have it. I don't know if I do, so I might just go underneath this right here. All right. And with this, I'm going to start by drawing a type of wave that is, mainly what I'm going to talk about are transverse waves. So I'll go ahead and write that down. And this is a wave that has motion. The particles move in the medium, move perpendicular to the direction in which the wave travels. So let's go ahead and define that. So the particles move in the medium uh, 90 degrees or perpendicular to the direction in which the wave moves. So what I'm saying here is this. If we are a transverse wave would be something, if you were to say take a string and try and draw someone's hand. Oh boy. Okay. And move the string up and down like this, right? You would create a disturbance that maybe looks like this. And this wave is going to move in this direction on this string because you gave it a disturbance here, right? That caused this wave, and this wave moved. The disturbance was up and down, right? Or you shifted the string up to create this disturbance here, while the wave moves 90 degrees to that, moves to the right. So the particles moved up while the wave moved right. So this is our 90 degrees, which we call this a transverse wave. All right, and these are the ones we're usually familiar with as our sinusoidal waves, our sine and cosine waves from math class. Okay, so let's go back to getting some of these characteristics here. All right, so characteristics of a wave continued here. Let's start by drawing a transverse wave. So I'm going to draw some axes here. We will put its height over the height of the wave over on the left, and let's go ahead and sketch this transverse wave, a sinusoidal wave, right? And talk about a few things here. This distance, or actually, let's start by talking about this midline here. This midline, right? This is called equilibrium. And the idea here is if there was no disturbance, that the medium would just sit at equilibrium, right? And that's what we would see. Okay, this distance, the max distance from that a wave is displaced from equilibrium, which is the same distance as this, and the same distance as this. This is called an amplitude. It doesn't matter if it's below equilibrium. So it is that distance right there. We can also talk about these locations right here at the top of this wave, and at the top right here, these are crests. So I guess I can put a little, it's kind of drew that kind of close. All right, so that location and that location are crests, and this would be a trough. All right, as we start to talk about standing waves, waves that don't move, right? There's that kind of wave, kind of like a jump rope, kind of is a standing, it looks like a standing wave. But we also have moving waves, and that's really what we've been talking about, right? A wave is a disturbance in a medium that carries energy. I added the word forward there. because it is traveling, right? It's a traveling wave. And but sometimes for a wave that isn't traveling, that might still look like this. We can talk about, and this is once again the height of the wave. We can talk about some of these points. When the wave is at the medium, we like to refer to these as nodes. And this is mainly for standing waves, right? Because if it's a traveling wave and it's just like this, right? It's just this disturbance right here and it's moving this way. I'm not going to talk about all of these as being nodes, right? Even though they are at equilibrium. I like to use nodes for a wave that maybe oscillates up and down but doesn't travel anywhere. And that's a standing wave. So these locations of equilibrium are called nodes. Antinodes are where we are at an amplitude, right? All right, so I had a phone call come through that ruined my video, but you can see that an antinode is also here at a trough or a crest right here. So mainly I like to use that for standing waves. Now, let's keep moving with some characteristics of waves. Maybe a couple more drawings. Let's go to the period of a wave, which is we've talked about before. It's capital T, and this is the time for the wave to complete a cycle or to move a cycle. It's the time per cycle. And so I think a drawing will help with this. So once again, we'll draw our axes. And notice we're going to add something to the x-axis, right? And I'm going to put time on the x-axis. And that's key when you look at these pictures of a wave to realize, is time on the x-axis or is distance on the x-axis? Because that matters, right? So let's go ahead and draw a similar wave to last time. It's going to look like this. Maybe a little different. And I'm going to go ahead and put some points on here. And the numbers are kind of arbitrary. I'm just making them up. All right. This, we can see from this graph that when we go from, say, crest to crest, that the wave is repeating, right? And that would be a cycle. So this time period, right? This period is what? Well, how long? Well, it goes from 1 second to 5 seconds. So in order for it to repeat, how many seconds is that? Well, it would be 4, right? So 4 seconds for the wave to repeat, right? Because at 1 second it looks like this, and then 5 seconds. At 5 seconds it looks like this again. So it took 4 seconds for that to happen. Now you might say, well, how does this relate to maybe a wave when you're at the beach or something? How would that? How does that work out, right? And so what I like to do here is kind of think of this wave as happening at a location. So some number of meters out into the water, right? You could think of this as the movement of a dog toy, right? This is how the dog toy moves up and down over time. Right? And so this is for a set location. So I'm saying maybe this is 10 feet out into the water, right? So 10 feet out into the water, this is happening to the toy. As time passes, the toy moves up and down as it stays at 10 feet out in the water, right? And this is its amplitude, or its height, or the height of the wave, right? From equilibrium, the displacement from equilibrium at different times for that dog toy. We like to call this a history graph because it shows what happens to the displacement of the wave over time, right, at a certain location. All right. What else can we add there? Let's talk about frequency. Because I think when we talked about period before, we talked about frequency. And so let's make sure we add that too. Frequency is lowercase f, and whereas period was time per cycle, or seconds per one cycle, right? Frequency is going to be the number of cycles per 1 second. So it's the inverse, right? And that really is our relationship here. So how do I want to say that? Well, what we can say is that if this is what frequency is, what's the frequency of this graph, right? And we can see that there is one cycle in 4 seconds, right? So I could write it like this. Okay, but that this says that frequency is supposed to be the number of cycles per 1 second. Well, let's do the math then, right? This is 1/4 or 0.25 cycles per 1 second. So what that says is in 1 second you went a quarter of the cycle, right? And in 4 seconds you would go the whole cycle, and that's why the period is 4 seconds. But in 1 second you only go 0.25 cycles. So this is the number of cycles per second. All right, and this is frequency. This is also has a SI unit of hertz. HZ, capital H, lowercase z, or I could just write 0.25 hertz. All right. Good. Let's add a little bit more to that before we move on, and let's just say and remind ourselves what the relationships are between period and frequency. So period is equal to 1 over frequency, and frequency is equal to 1 over the period. So both of these are correct, and that means that there is, try and move this up a little bit, an inverse relationship between period and frequency. All right. Good. Let's move on to wavelength. All right, so we'll do another drawing here. Once again, drawing the axes. But this time, let's put distance over here, right? Distance from shore for the dog toy, right? And let's go ahead and draw the wave. It's going to look similar to last time, but it's going to be different. I'm going to make it actually look pretty identical. But I'll make it different because I'll say that this is 2, and this is 4, and this is 6, 8, 10, 12, 14. You get the idea. All right. So in this case, when a cycle happens or the wave repeats, right? Say from trough to trough, or crest to crest, or node, skip a node, next node. I should probably draw all that really quick. That this distance, right? Because now it's a distance in meters, is a wavelength. And a wavelength is represented by the Greek letter lambda. Should probably write that down. I'm not sure if that's uppercase or lowercase lambda, but it's lambda. All right, so this is a wavelength, but we can see, like I said, it's also the same distance, which is what? What is this distance? Well, it goes from 2 meters to 10 meters, so that would be what? All right, you should be saying 8 meters. So this is going to be 8 meters for my wavelength. But look, from trough to trough, what's that distance? 6 to 14. That's 8 as well. What about from node, skip a node, next node? All right, this kind of looks like a complete sine wave, right? You went up, then you went down, and then you're back. So it's a wavelength is like a wave going there and back, right? That is a cycle when the wave travels there and back. If I had a mass on a spring, because I think we talked a little bit about this, if we were to put a mass on a spring, and maybe it started at equilibrium, a cycle for this mass would be for if it started here, would be to go all the way back to equilibrium, then all the way down, and then all the way back. So it would be, the period of it would be the time it takes for the mass to go from maybe this displacement past equilibrium to this displacement, right? Back to equilibrium, and then all the way back. So it'd be the time it takes to go there and back. And so a wavelength is the distance it takes for the wave to repeat, right? And it's kind of like it's going from up there and then back, right? So that distance is 8 meters. But like I was saying, node, skip a node, next node, right here would also be a wavelength, right? And right here would be a wavelength. So, and that's 8 meters, right? 0 to 8. I don't know where my 0 is. That's 8 meters, 6 to 14. That's 8 meters, 2 to 10. Okay. Good. So how does this relate to the dog toy? Well, maybe this is, you're at the beach, right? Again, you throw the dog, its toy, and this time the dog toy goes out to 10 meters. So maybe the dog toy is sitting at the top of this wave right there, right? And you take a picture of the water, right? And the water looks like this, right? So you're standing off to the side and you can see from the shore right here to 10 meters out, and you can take a picture of this water wave and it looks like this. So what we're doing then is we're saying that this is at a certain time, some number of seconds, right? That you snap this picture. Maybe it was at time 0 seconds. Maybe it was at time 5 seconds. Because we know the dog toy is going to move up and down on its wave, and it's not going to come towards shore, and the dog's not going to get it because you threw it too far, and you're going to have to go get it. But this is at some time you snap this picture, and the dog toy is, we'll just say is sitting, or is it sitting? I don't know, resting, is sitting at a location. So we can refer to this kind of like a snapshot, right? And so that's what we call this. We call this a snapshot graph. And so we make a graph like this for a particular time that shows what the wave's displacement is doing at multiple locations. Whereas in a history graph, we looked at just one location, right, where the dog toy was. Maybe this is 10 meters. And we watched what the toy did, its amplitude over time. So this is tricky, right? So what we're seeing is that the amplitude or the height of the wave is dependent upon time, right, is a function of time, and is a function of distance from shore, both. So we have a quantity that depends on two variables, and we don't see that a lot, right? And so anyhow, what else can we say? So let's define wavelength. We'll say the distance the wave travels in one cycle. All right. So like we said, it could be crest to crest, trough to trough, node, skip a node, next node, and the same is true for period. I didn't label that back here, but I can show you really quick. So trough to trough, look at that. T equals 4 seconds, right? Same as before. And then node, skip a node, next node from 0 to 4. So this would also be a period. Now, noticing that it's that us thinking of this cycle as a period depends on this x-axis being time. And when the x-axis is instead distance, then a cycle is a wavelength. All right, so that's kind of tricky in itself. All right, I think we are good right there. Let's kind of bring this together with one equation. All right, so let's use some of these ideas to write a fundamental relationship here. And this is for sinusoidal waves. But really it's going to apply to all waves that we talk about. And on the AP test, this is the only equation they give you, really, for waves. And so let's start by writing our velocity or speed formula, v equals d over t. And let's remember that during a time of one period, so when t equals t, each crest of the wave, right, each cycle travels one wavelength. So what I'm trying to say there then is if each crest travels one wavelength, then the d is equal to lambda, right? So we have v then is equal to lambda over t. Now let's also remember that, let's split this apart. I think that might be easier to see. So we'll have 1 over t, right, times lambda. And let's remember what 1 over period is, right? And that is frequency. So here is our equation right here. So the velocity of a wave is equal to the frequency times the wavelength. And this is a super important equation. And like I said, it's the only one to show up on the AP physics test about waves. That's how important it is. And so what we have is our velocity of a wave. Units there are meters per second, is equal to the frequency. And that's going to be in hertz or cycles per second. Times the wavelength. And that's going to be in meters. And it's probably worthwhile to mention here, let's slide this up a little bit, that cycles are unitless. So really, frequency of hertz really has units here of per seconds, right? Or seconds to the -1, or 1 over seconds. So when we multiply 1 over seconds by meters, we get meters over seconds, or meters per second. But that's kind of yeah, that's what a hertz is. Cycles are unitless, and so it's really just per seconds, or 1 over seconds. Okay. All right, so a good question to ask here then, with this fundamental relationship that velocity equals the frequency times the wavelength, is does increasing the frequency, right, increase the velocity of the wave? And you might say, well, this looks like a proportional relationship, right? And if I increase this, it should definitely increase the velocity. But does that make sense? You can think of it this way. If you were, say, playing a piano, a note that has a higher pitch has a higher frequency. And so if you play a higher note on the piano, does that note travel to your ear faster? And that's a good question to ask, right? It doesn't seem like it would, but if you look at this equation, you think that if you double the frequency, right, you should very well be able to double the velocity. So let's look at what happens when we double the frequency. If we make a couple graphs here, let's make this first one. And if you don't want to write this down, this proof right here, you don't have to. You can just watch this part, and that's fine. Let's make the first one versus time. And I'm going to go ahead and just make, I'll try and keep it simple and just make a shorter wave right there. And we'll say that this is, I don't know, we'll say 2 seconds, 4 seconds, 6 seconds, and 8 seconds. So how do we find the wavelength here? Well, the period here, because this is time. The period would be crest to crest, but remember I showed you another way to find that same distance, and that is to go node, skip a node, next node. So this is also 1 period. So this is t. And the period here is 8 seconds, right? This distance here, node, skip a node, next node. Just to prove it to you, I can make this go longer, right? Check it out, 10 seconds, right? And then this can be 12 seconds. And look, this distance right here, right, from crest to crest is the period, and that is from 2 to 10 seconds, that is 8 seconds. So it's the same as this. Okay, so anyways, the period is 8 seconds. Well, let's make a wave that is twice as frequent, right? So what that means is that these crests are going to happen twice as often, right? So it's going to look like this. So notice how it's much more frequent, right? We're doubling the frequency, so these crests are more frequent. Okay. All right, pretty good. Let's find, hopefully you can see the color there. I'll try and make this wave stand out a little bit, give it a little bit of, I don't know, texture. And now you can see that, so it doesn't look like the black wave, but it actually is green. I just don't know how well the color's coming through on the phone. Okay, so check it out. On that green wave then, right? Let's find a crest. Let's find the next crest. What is that time interval? Well, that's the period of the twice as frequent wave, right? And so what we're saying is, looks like it goes from 1 second there up to 5 seconds. So it looks to me like, right, this is 1 and this is 5. So it looks like the period there is 4 seconds. So what we're saying is when we doubled the frequency, right? So we're saying we took the period went from 8 seconds to 4 seconds, but can we prove that the frequency actually doubled, right? Besides me just telling you, oh yeah, well I drew it this way, so it had to double. Well, let's calculate it really quick, right? So when t... Okay, so I was interrupted there for a second. Our formula here is frequency equals 1 over t. So when t equals 4 seconds, frequency is going to equal 1 over 4 seconds, which is 0.25 hertz. And when the period is 8 seconds, then 1 over 8 seconds, I think that's going to be 0.125 hertz, 1/8. Yeah. Okay, so we can see then that the frequency does double, right? When I drew this green wave with the period equal to 4 seconds. When t equals 4 seconds, 0.25 is twice as frequent as 0.125, right? 0.125 times 2 is 0.25. Okay, so well, that's great then. So we're seeing what a wave that's twice as frequent looks like. But what about, so if I double this, I should be able to double velocity, but what about the wavelength? And we can't really get the wavelength from this graph because this is time over here. So this distance is the period, right? So we need a new graph. So let's draw a very similar looking wave, sinusoidal wave. And I'm going to go ahead and make it look a lot like the last one. But it's different, right? Because this is going to be x in meters. And just to continue to make it different, I will call this 1 meter, 2 meters, 3, 4, 5, 6. Okay, so a good question to start with is what is the wavelength of that wave? And we would say, well, crest to crest. Let me see if I stick with this. Crest to crest, the wavelength is going to equal, it goes from 1 to 5, so 4 meters. Let's now make this wave twice as frequent, right? And so what that means is this wave needs to occur twice as often, right? So instead of having the first crest here at 1 second, I'm going to have the first crest at, at half a second. Just like I did before with the green wave. You know, it's pretty, but I'm making this one red. Okay, so you can see these crests are occurring twice as often is the idea because we're doubling the frequency. Now let's look at the wavelength of this new wave when it's twice as frequent. All right, what would that wavelength be? Well, it goes from right here, which is, I think, 0.5, yeah. And then this is 2.5. So it goes from 0.5 to 2.5, which is a distance there of 2 meters. So what we're seeing is that doubling the frequency, right, when these waves happen twice as often, does what to the wavelength? Well, it goes from 4 to 2, so it halves it. So we're saying then that when this is doubled, this gets halved. And if you multiply f by 2, but you have the wavelength, you can see where this is going, right? 2 times a half, 2 halves is just 1, and you just end up with frequency times wavelength. So what this means is, does doubling the frequency double velocity? And the answer is no, right? You can't, the velocity is constant, right? When you double the frequency, you have the wavelength. And the same is true when you double the wavelength, you have the frequency. So velocity of a wave is constant for a medium unless you change the medium, and that's worth writing down. So let's do that. So what we want to say then is this, that the speed of a wave is constant for a given medium. And the medium or temperature has to change for the speed to change. If it was a string, you can change its linear density. So you can change how thick the string is or what type of material the string is made out of. But just changing the length of the string isn't good enough. So we're not totally worried about that right now, but that's something that comes up in AP Physics. So increasing the temperature does raise the speed. So we're saying that air at 20 degrees Celsius, which is about room temperature, 68 degrees Fahrenheit, has a velocity of 343 meters per second. And this is a good velocity to remember. And so this is the speed of sound. So this is V sound, and that's not written on there, but I can write that. And that's in air at 20 degrees Celsius. The speed of sound in air at 0 degrees Celsius, which is 32 degrees Fahrenheit, which is when water freezes, right, is equal to 331 meters per second. So as the temperature of air gets colder, the speed of sound is less. All right. So what about, well, how else can we change the speed of sound? Well, we could change the medium, right? So it doesn't have to be air. What if it's a liquid? What if it's through water you hear something, or through a solid, right? That would be like if you fell asleep in class and your head was on a desk and somebody knocked on the desk, right? The sound sounds different when it travels through a desk as opposed to listening to it through air. So what we can see, and these are just kind of general, I had a table I was going to show you, but I think I'm going to hold off on that. Sound travels faster through liquids. Velocity of sound in water about 1,480 meters per second, and even faster through solids. V sound in granite is 6,000 meters per second. So it's just kind of worthwhile to note. Now, one thing I just like to mention is if I was talking to somebody in the same room and I decided, I was like, well, I really want to convey my message to them quicker. I would like for that sound to reach their ear faster. So I'm going to yell what I'm saying. Yelling does not help the sound get there quicker. Think about it this way. Like if you're watching the fireworks on the 4th of July, the fireworks still have a delay when you hear them and when you see them, right? If you're watching them from a distance, right? You see all the fireworks because the speed of light is so fast, 3 times 10 to the 8th meters per second, then you hear them all like a few seconds later, right? And it's similar to lightning, right? You see the lightning flash in the distance, you wait a little bit, and then you hear the rumble of thunder. Okay, so, and you can actually use that to calculate how far away a lightning strike is, and maybe we'll do that next week. But anyways, a louder sound wave has more energy travels the same speed as a sound wave that is quieter. So when you change the loudness, when you change the intensity, you're changing the energy, you're changing the amplitude of the wave, you're changing the height of the wave. You are not changing the speed of the wave. The speed of the wave is dependent on the medium, right, which is air, and then that medium's temperature. All right. Okay, so let's move on from there. Let's go ahead and talk about what happens when waves interact. All right, so let's talk about what happens when two waves meet and how they're different than particles, right? Particles meet, two particles hit, they reflect, they bounce off of each other. That's what we would expect to happen, but that doesn't happen with waves. Now, waves that happens at boundaries, meaning if you were in a certain room and maybe you were singing or playing a musical instrument or talking, there's certain acoustics because waves reflect at boundaries, right? But they don't reflect when they hit other waves. You know, we wouldn't go to a concert and expect to hear the guitar reflecting off of the bass guitar, reflecting off of the drums, or reflecting off of the cymbals, right? So waves don't reflect off of waves. That's one of the first things to note. So, meaning sound waves don't reflect off of other sound waves. But this is true of light too. Light doesn't reflect off of other light. This is because waves aren't matter traveling, right? Waves are energy that's moving through the medium. And so something interesting does happen when waves meet, but it doesn't involve them bouncing off of each other. Instead, the waves are going to hit each other, amplify constructively or destructively, and then pass through unaffected. So we like to call this by two names. We call it superposition or interference. Either one is correct. Why are there two names? I don't have a good answer for that, but there are definitely two names for it. What this is superposition or interference is when two or more waves are at the same location, right when they meet. The displacement of the medium at that point is the sum of the displacements due to each individual wave. So what this is saying is the waves, when they meet, are either going to add together and make a larger wave, or they're going to destructively interfere and cancel one another out. And this is the idea behind noise canceling headphones, right? That your headphones are going to take the sound waves from out in the environment that are around you and then send out a canceling wave, send out a wave that is exactly opposite of the wave that is coming in from the environment. So that's weird, because what that means then is that noise canceling headphones cancel sound with more sound waves in order to make it quieter for your ear. So they're using additional waves, additional sound to make it quieter. All right, that's kind of crazy, but that's what's going on with noise canceling headphones. So this idea of superposition or interference even happens with light waves, sound waves at a concert, obviously, water waves, yes, but even light waves. So that's kind of an interesting idea too, because that's saying that light, when it hits other light, can create dark regions where the light cancels out other light. And that's one reason we know light is not just a particle, it's also a wave. So light exhibits both properties, right? Particle being photons of light, and then a wave because light exhibits interference. Light hitting other light can cancel out and create dark regions. That's pretty awesome. All right, so let's talk about how we see this then. Constructive interference and destructive interference. So two ways here. Constructive interference is when displacements in the same direction from equilibrium, we add these two displacements and the resultant wave is larger. So we'll look at an example of that, of constructive interference. So here's one right here. This is a rough sketch. So obviously we can do way better than this, but this is always going to be a model. So it's not going to be perfect. And but this is kind of the idea. We have two, maybe these are one block high waves, right? And when they meet and hit, assuming they will meet and hit, because sometimes the waves can just shift past each other and never meet and hit, right? But if they do meet and hit, you would have a two block high wave when they meet, but then afterwards, no permanent change to the wave. So the B wave is still one block high, and the A wave is still one block high, and the B wave is still heading left, and the A wave is still heading right. All right, so this would be constructive interference. Now, would it matter if this wave was down and this wave was down? And the answer is no, right? So we can also draw a similar situation where we have constructive interference, but these are two one low waves, right, are going to meet and create a two low wave, and then they're going to move past each other unaffected. So that's kind of the idea, that the change that you see in these sound waves doesn't it amplifies for a split second, but then afterwards there's no permanent change. All right. Obviously the waves are going to get smaller over time, but that's just because the energy is dissipating. But what this is saying is that the waves don't affect each other than after the time of interaction. So they affect each other when they interact, but afterwards not at all. Okay, let's look at destructive interference. Okay, so destructive, now the two waves are going to be on opposite sides, and when they hit, right, you might say I didn't draw anything. Well, that's the idea, is they canceled each other, right? So the one high canceled the one low. It's like a positive one meets a negative one, and we see zero. And then, but afterwards they pass on. This is still a one high heading left, and this is still a one low heading right. So after the two waves interfere, they pass through unaffected. All right, so this is a rough example of destructive interference. Okay, so what I want to do next is do some example problems of interference, and then some from the homework. The homework's going to be 2 or 3 worksheets. The example problems that I want to work on, I'll probably put these in a separate video. I want to help start number 9 and 10 from this wave worksheet. And I also want to, this wave worksheet right here, where it starts off just using V equals frequency times wavelength pretty much on the front, has an example of interference that I also want to work through. The third worksheet, which has further examples of interference, kind of looks like this. And then I may do one from here also. So I'll put that in a separate video. But that's it for this week as far as the ideas we're covering.